Hello, this is Stuart Mason for Math E156-156. We're doing script 10b. This is a beta binomial Bayes example. So the first thing we're going to do is just familiarize ourselves with the beta distribution. It has a pretty ugly analytic form for its density function. A lot of gamma functions involved. Something that looks kind of difficult to integrate. Fortunately, R just lets us skirt that problem with its d beta function, and we're just going to look at a couple different values of the parameters on the interval 0 to 1. So there's alpha equals beta equals 12. Here's alpha equals beta equals 1/2. This is known as the arcsine density function. Here's 1, 1. This is a nice flat uniform distribution. So kind of a surprise, but the standard uniform distribution is actually just a special case of a beta distribution. These next three examples all have the same mean. It's going to be a quarter in every case because beta is 3 times alpha, but the variance will be ever decreasing. So in blue with different line types, we have one that the expectation is 0.25, but you see it's a pretty wide range of values. And then as we tighten it up, we're going to keep clustered around 0.25, but get ever higher and ever thinner curves. And then finally, we have something that in the limit approaches what the book talks about, this improper prior that blows up with alpha equals beta equals 0. So Paul gets close to 0 so we can have some idea of what we're looking at. And he calls this a non-informative prior. You see it in gray down here. And basically, we're assigning almost no probability to the values in the middle here, and very high probability that I think blows up to infinity at 0 and 1. And you can kind of reason how this is similar. Like, this is basically we don't know anything, right? We're willing to allow that there's a very high chance the probability is 0, and we're willing to allow that there's a very high chance the probability is 1. And then the legend function I explained in the last script, but I noticed that I forgot to mention the LTY. So this is line type equals 1, and that's what makes the lines here be these nice sort of unbroken solid lines. Okay, so now let's clear out this mess on the right and just pick one beta distribution with alpha 3, beta 7. So here Paul is defining his own density function, basically just using the gamma function that's built in, creating a function of x that spits back the beta density, and he's going to plot that in red, and sure enough, this is close enough to what R is using for its d beta. So we're going to integrate it from 0 to 1 to make sure that it has an area of 1, which it does, as all PDFs should. Then we can integrate the density times x to get the expectation of x, and it says that's 0.3, and the definition also gives us 0.3. He does the same thing with the variance, and those agree as well. This next step I take umbrage with. So Paul says, given a desired expectation and variance, we can create a beta distribution. And so the book says, use MATLAB or whatever to solve this system of equations, and Paul says, well, that's silly, you can do it by hand. And I say, well, that's also silly. To take an expectation and variance and tailor your beta distribution to that is essentially the method of moments, which isn't really modern, and it overlooks the power of the personal computer. So oftentimes you don't have an expectation and variance, you have data. This happens to me at work quite a bit. You have different success probabilities, then you want to assign a distribution to what you're likely to see on a given day. And the best way to do that is with maximum likelihood estimation. Now, a beta distribution's MLE estimators don't have nice closed forms that you can write down, but that doesn't bother a computer, and there's all kinds of R libraries that you can find with a quick Google search that basically take a vector of data and spit back two estimates for the parameters, and also all kinds of other information that's helpful, like the standard error of those estimators. But so this is obviously what we're going to be doing in this course, and this is plenty for understanding the concepts. But if you ever find yourself needing to calculate alpha and beta, I recommend looking for a library to help with that. I think R has a library built in called MASS, M-A-S-S. That's good at this. Anyways, so now that I'm done ranting, let's give an expectation and variance. Let's calculate our sort of method of moments, alpha and beta estimators. Of course, they give us the right answers for the expectation and variance. That's unsurprising. And here is sort of an estimated beta that might describe the data from which we got this expectation and this variance. So now, let's do some statistics. We're going to take the example from the book and cut it by a factor of 10. So pretend we surveyed 20 students, and 11 of them say, yeah, I watched The Daily Show. The textbook says with Jon Stewart, I guess it's showing its age, because Trevor Noah is the host of The Daily Show today. But, so, if we start with a uniform prior, which is sort of another uninformative, right, you're not making any assumptions, it's equally possible that any of the probabilities are the true proportion, alpha equals beta equals 1. And then Paul is skipping right past the hard work of using Bayes' theorem and going directly to what he knows the posterior distribution is going to be, and he knows that alpha will be the number of yeses plus the original alpha, the prior alpha, and beta will be the number of no's plus the prior beta. That's what gives us this 12 and 10, and this is the resultant posterior distribution that we're going to put on the value of the proportion of students on our campus who watch The Daily Show. And just for reference, this is the prior that we started with. So we've improved the estimate a great deal with our experiment. And then he uses the quantile function to get the quantiles, the 2.5% quantile and 97.5 quantile for a distribution with alpha 12, beta 10. And this is basically our credibility and interval. And might be nice to go a step further here. And add these to the plot. So this is a kind of plot that I actually look at work a great deal, and basically the overlap of two different treatments or something. You want to know if one is more successful than the other. You can plot their distributions and see where their centers are, and then you can also see what kind of window you put on the true value for each one. So. Okay, so then the textbook says, well, what if you could do better than a uniform prior? What if you had some data about a national poll and you're willing to believe that your campus is a microcosm of the national? The national poll suggests that 58% watch the show, and they have put some fuzziness on their estimate, and they're saying the standard deviation is 0.03. So Paul says, and this is actually maybe an argument for using the method of moments instead of the rant I just went on, where maybe you don't have the data, you only have an idea about the expectation and the variance, fine. So that yields these estimates for alpha and beta, which this isn't always the case in Bayesian statistics, but it's really great how these have kind of nice interpretations as the yeses and nos. Basically, this poll probably sees somewhere in the neighborhood of 156 yes and 113 no's, and that's when we try to back out and put a prior on there, what they're reporting, we get something that we can interpret. So let's draw it. Okay, so based on the national data, and something like 300 respondents is a pretty good sample size, so this is pretty tall and pretty tight. And this is going to be our prior. So if we update this prior with now the data from the previous example, but a factor of 10, so we're adding 110 yeses and 90 nos. Here's the posterior. So the proportion on our campus is a little bit less, so this has walked down a little bit. And now that we have more data than ever, it's tighter and taller. So I do want to point out this is a wonderful shortcut, but keep in mind why this works. This comes directly out of doing the algebra and applying Bayes' rule to the relevant distributions, and then you get this nice result that you can keep the shortcut. But I want to point out that the work we did to get here was important, because there's not always these nice, easy shortcuts for all the priors and posteriors that you can encounter. And again, we can whip up a credibility interval, and it looks like it's going to be centered around high 50%. If we round alpha and beta, then this is similar to a poll with 470 respondents. So about 200 from our experiment, about 270 from the Book's experiment. And if you just treat this as a binomial situation, you can construct a frequent test confidence interval, and you get something quite similar. It's always reassuring when you do something two different ways and get answers that are close, although it's a little bit disappointing to me in this case, because whenever you learn a new method, you're hoping that it's going to be better and have more power than your previous methods. And there are situations where that's going to be true for Bayesian statistics, but really this is just another tool in your toolbox. It's not, unfortunately, much magically better than the statistics we've learned so far, but it works. So I hope that was helpful. Looking forward to seeing you guys on Wednesday, and I'll meet you back here for script 10C.